On a dark ship deck, as you look out across the sea, two clusters of lights glow on opposite ends of the horizon. On the left, the street lights of a city. On the right, an entirely different continent. Between them lies nothing but a dark, silent strip of water. And across its surface, the lights of passing ships drift slowly by, like invisible needles trying to stitch two continents together. This is the Strait of Gibraltar, the closest point where Europe meets Africa. A strong swimmer could cross this distance. A bicycle could cover it in less than an hour. Yet for nearly a century, humanity has failed to build a permanent crossing here. Not for lack of trying. Every attempt has been stopped at the very same point. In the summer of 2025, strange instruments were lowered to the floor of these quiet waters. Deep-sea seismometers. They were placed in silence, and they began working in silence. We'll explain what they were listening for in a moment. For now, just know this. Beneath this narrow strait lies one of the most stubborn engineering puzzles on Earth. For a century, the same question has been asked, and silenced by the same answer. But by the end of this video, you'll understand why that puzzle finally seems within reach. At first glance, it isn't obvious what this strait has to do with everyday life. But once you look at the numbers, the picture changes. Every year, 12.8 million passengers cross the Strait of Gibraltar by ferry. That means, on average, 35,000 people every single day depend on a ship to travel between two continents. The population of a small city wakes up each morning at the mercy of the same stretch of water. Because this crossing depends on the wind. The strait's two famous winds, Levante and Poniente, can become so powerful on certain days that ferry services are canceled entirely. A family visit, a business meeting, an exam, everything is left to the wind's decision. The same winds also stop freight. Components manufactured in Morocco's automotive factories reach assembly lines across Europe by passing through this narrow channel. The port near Tangier is one of the largest container ports on the continent. Yet crossing to the opposite shore still depends on a ship, a work shift, and a weather report. The result is simple. Without even realizing it, millions of people on two continents live according to the whims of this strait. A component inside your phone, the fabric in your wardrobe, a product that arrives late on the shelf. They all trace back to this 14-kilometer strip of water. And this is where things become interesting. Two continents share one of the busiest trade routes on Earth, separated by such a short distance. On paper, closing that gap doesn't seem like it should require an extraordinary leap in engineering. This is where the story takes an interesting turn. Because the project that has been discussed for decades and shelved time and again is no longer just a dream. In June 2025, Herrenknecht, the German engineering company that leads the global tunnel boring machine market, delivered a report commissioned by the Spanish government. It sought to answer one simple question. Could the most challenging geological section beneath this strait now be crossed safely using today's technology? The answer was yes. This wasn't a promotional document. Herrenknecht's business is selling tunnel boring machines. Unrealistic optimism doesn't work in their favor. If anything, they have every reason to be realistic. And their conclusion was that passing beneath the Camarínal sill, the most complex section of the strait, is now technically feasible. This ridge lies beneath waters, reaching depths of 475 meters, where solid rock is intertwined with clay, creating one of the world's most demanding examples of mixed ground geology. That number may sound abstract. To put it into perspective, it's roughly the depth of a 30-story skyscraper turned upside down and buried beneath the ground. The significance of this conclusion is enormous. For the first time in human history, Europe and Africa could be permanently connected by a train journey lasting just 30 minutes. The entire route would stretch about 65 kilometers. But the real challenge has never been its length. It's how to bore through the 28-kilometer underwater section. So how are engineers finally solving a problem that remained unsolved for decades? Today, the ferry crossing takes about 90 minutes in good weather. That doesn't sound too bad. But in reality, those 90 minutes aren't a reliable number. They're an estimate that depends on whether the wind decides to cooperate that day. Some days, it's 90 minutes. Some days, there is no crossing at all. The tunnel project changes that completely. A fixed, scheduled train journey lasting just 30 minutes. No wind, no waves, no cancellations. The timetable becomes something people can actually rely on. That has two very different impacts on everyday life. The first is for passengers. Spain's high-speed rail network, AVE, and Morocco's Al Borak, the first high-speed railway on the African continent, could theoretically be connected to the same rail system. That would make it possible to travel between two continents on a single ticket, with only a few transfers. From an engineering standpoint, reaching Madrid from Casablanca on the same day appears entirely feasible. Of course, full integration of the rail networks, scheduling, and border procedures still depend on many other factors. So it's more accurate to see this not as a promise, but as a possibility that is finally within reach. Even today, that journey isn't this predictable by air. The second impact is on trade. Once the tunnel is completed, it is expected to carry around 13 million tons of freight every year. To put that into perspective, that's the equivalent of roughly 700 truckloads of cargo every single day being entrusted to rail instead of the sea. Morocco's rapidly growing automotive industry would no longer depend on ships to connect with European supply chains. It would depend on rail. Today, a component leaving a factory may end up waiting at a port through a work shift or for a favorable weather forecast. With the tunnel, that same component would depart on a fixed schedule along a fixed route. But there's an interesting detail here. Engineers are designing this route exclusively for trains, not for cars or trucks. There will be no road tunnel. And the reason isn't a simple one. At these depths, building a road tunnel creates a ventilation challenge that is almost impossible to solve with current engineering. And that detail leads directly to the very problem that has delayed this project for decades. A truck driver waits at the port of Tangier. The ferry is docked at the terminal, but no one knows when it will depart. The poniente wind has shut the strait down. He glances at his phone, then back at the sea. There's nothing he can control. Maybe 3 hours, maybe 12. The wind alone will decide when his cargo reaches the opposite shore. This scene repeats itself thousands of times on both sides of the strait. And it raises the real question: how can such a narrow, such a short stretch of water still remain uncrossed? Since the official agreement was signed in 1979, 47 years have passed. Nearly 50 joint committee meetings have been held. Millions of euros have been spent on feasibility studies over the decades. And yet, not a single meter of permanent infrastructure has been built. Why? The short answer is this. These waters combine 4 engineering challenges that have rarely, if ever, been encountered together. One is geological. One is depth. One is seismic activity. And the fourth is the one almost no one talks about out loud. We'll get to that in a moment. The first obstacle is the ground itself. Beneath the strait lie soft, water-saturated clay channels, overlain by fragile, unpredictable breccia rock. And beneath those, in complete contrast, sits extremely hard metamorphic rock that resists even the most powerful tunnel-boring machines. For a tunneling machine, it's like drilling through mud and granite at the same time. Previous generations of machines simply couldn't do that safely. The 2025 report concludes that a new generation of mixed-shield tunnel boring machines, designed specifically for mixed ground conditions, can now overcome this challenge. The second obstacle is depth. At the shortest crossing point, the Gibraltar Canyon, the seabed plunges to nearly 900 meters, making that route completely unsuitable for a tunnel. The selected alignment instead passes beneath the Cameronal Sill, where the maximum depth is reduced to about 475 meters. Even so, that's more than 6 times deeper than the Channel Tunnel. On paper, it's an intimidating number. The solution is to excavate an exploratory gallery before the main construction begins, gathering geological data meter by meter. In other words, not drilling blindly, but mapping the ground first. The third obstacle is seismic risk. The strait lies on the boundary between the Eurasian and African tectonic plates, along the Azores-Gibraltar fault zone. This fault is no stranger to history. It was the source of the catastrophic 1755 earthquake that devastated Lisbon and claimed an estimated 30,000 to 40,000 lives. That's exactly why those seismometers were placed on the seabed in 2025, to understand how the fault actually moves. The engineer's answer is not avoidance, but flexibility. The tunnel is expected to incorporate flexible joints between its segments, allowing it to absorb seismic energy, along with continuous earthquake monitoring systems. The question is no longer, will there be an earthquake? It's, when it happens, how can the tunnel bend without breaking? The fourth obstacle is the one almost no one talks about, because no one likes saying the number out loud: money. The project carries a price tag of more than 8.5 billion euros for the Spanish side alone. That's close to the annual defense budget of a medium-sized country. And how an investment of that scale ultimately pays for itself remains a question that most technical reports leave in the background. But this is exactly where things become interesting. Relations between Spain and Morocco have improved significantly since 2022, and the two countries will co-host the 2030 FIFA World Cup. For the first time in nearly 50 years, the technical, political, and economic winds are all blowing in the same direction. So if all 4 of these obstacles can finally be overcome, what remains? Imagine a steel cutter head making its first contact with rock, 475 meters beneath the Mediterranean Sea. There is no sound, no light, only immense pressure and a slow, patient advance. Above, ferries continue crossing the surface, completely unaware of what's happening below. Now let's descend into the engineering itself. The 2 geological formations beneath the strait differ in hardness by as much as 3.5 times. On one side, ground that's almost as solid as stone. On the other, layers with the consistency of soft mud. The same machine must handle both, sometimes within the very same day. That's why engineers are no longer relying on a single giant tunneling machine. Instead, they plan to excavate a narrow exploratory gallery first, mapping the ground step by step before moving on to the main tunnel. First, listen. Then, cut. Why does that matter? Because for the first time, it's not a dreamer making the claim. It's the world's leading tunnel boring machine manufacturer saying that this crossing is physically achievable. So why build a tunnel instead of a bridge? Because even at the strait's narrowest point, a suspension bridge would need a main span approaching 5 kilometers to allow international shipping to pass beneath it, more than twice the span of the 1915 Çanakkale Bridge in Turkey, the current world record holder. On top of that, engineers still don't have a satisfactory solution for the wind-induced oscillations that such enormous suspension cables would experience. That's why the bridge concept was quietly abandoned decades ago. Beneath the strait had become a more reliable solution than above it. Now let's move to the environmental layer. The Strait of Gibraltar is the only natural exchange point between the Atlantic Ocean and the Mediterranean Sea. Warm, salty Mediterranean water flows outward near the surface, while colder Atlantic water moves inward along the seabed. This two-way current also sustains one of the world's busiest migration routes for whales and dolphins. So could building a tunnel disrupt that balance? Engineering teams are already planning measures, such as ensuring that excavated material is never released into the path of these natural currents. Because here, a single wrong decision wouldn't just be an engineering mistake. It could come at the cost of an entire marine ecosystem. Now, let's look at the economics. When both the Spanish and Moroccan sides are included, the total investment could reach 15 billion euros, with 8.5 billion euros of that belonging to Spain alone. It sounds enormous. But the Channel Tunnel, completed in 1994, cost almost the same in today's money. In other words, this is not an unprecedented figure. It's the kind of investment that has been made before, and one that ultimately proved its value. When we reach the human and political layer, the picture becomes more concrete. This project requires political commitment in Spain that can survive at least 3 election cycles. Territorial disputes over Ceuta and Melilla remain unresolved. Migration pressures generate both support for the project and opposition to it. Yet despite those challenges, the Spanish engineering company INECO was commissioned in November 2025 to prepare the preliminary design, with delivery scheduled for August 2026. After that, the first exploratory drilling tender is expected in 2027. This is no longer just an idea, it's a project with a timeline. And this brings us to the seismic layer. The strait lies along the boundary between the Eurasian and African tectonic plates, on the Azores-Gibraltar fault zone. This fault generates earthquakes through a combination of horizontal strike-slip motion and deep thrust movement. Joint research by Portuguese and Spanish seismologists has yet to fully explain how these two mechanisms interact. If the tunnel's natural vibration period were to coincide with the frequency of an earthquake, the shaking would not dissipate, it would amplify. Eurocode 8 still does not provide a universal design framework that fully addresses this specific uncertainty. This remains an active field of engineering, where the standards themselves are still evolving. Taken together, all of these layers reveal something important. What makes this project possible isn't a single breakthrough technology. It's the point where multiple engineering disciplines finally converge and reinforce one another. If political stability and long-term funding come together, the scene in the mid-2030s could look something like this. A passenger departing from Madrid could reach Casablanca on the very same day via a connecting high-speed rail network. Smooth schedules and seamless border procedures are still assumptions, but from an engineering perspective, they are no longer impossible assumptions. During the 30-minute crossing, the view outside the window would be nothing more than the tunnel wall. Yet on the other side of that window, the same lights once seen from the deck of a ship would still be waiting. A Moroccan student could travel to a university in Spain without depending on the wind. An exam that today might be missed because a ferry was canceled could become a concern of the past. A truck driver would no longer spend uncertain hours waiting at the dock, but instead move along a scheduled railway. A container leaving the port of Tangier Med would reach Europe by train rather than by ship. A product waiting in a warehouse would arrive on store shelves sooner. None of this means everything will be perfect. Timetables can slip, costs can rise, political winds can change direction. But the rare convergence of improving political relations and maturing engineering has created a unique moment, one that could finally change the destiny of this strait. And at this point, one question naturally comes to mind. If all of this has truly become possible, then only one question remains. Looking back at everything we've covered, the picture becomes much clearer. The geological challenge is now an engineering problem that modern machines are capable of solving. Seismic risk has become a variable that can be analyzed, anticipated, and absorbed through design. The cost is on a scale that history has already shown can be justified and recovered. Even the political climate has shifted in the project's favor for the first time in years. So perhaps the question we asked at the beginning of this video was the wrong one. The real question was never, is this crossing possible? Engineers have been searching for that answer for decades, and today they finally have one. The real question is this: was geology ever truly the barrier separating those two clusters of lights seen from the deck of a ship? Or was geology simply the easiest excuse for something else? A lack of political will. At this point, there are honestly two equally compelling ways to interpret the story. On one side is the argument that the fault zone and the extreme depths genuinely required this much time, that engineering has only recently caught up with the challenge. On the other is the view that the technology has been ready for years, and that the real obstacle was never engineering at all, but a lack of political will and the courage to move forward. Both perspectives are convincing. Which one carries more weight is something each viewer can decide for themselves. If you'd like to join the discussion, share your perspective in the comments. Those lights on the ship's deck are still there. On the left, the streets of a city. On the right, an entirely different continent. But now we know that the dark strip of water between them could one day become a railway. Perhaps the real barrier was never the distance. There are more projects we haven't told you about yet. Projects that even the engineers working on them describe as crazy. We'll explore them in the next video. Turn on notifications and be among the first to see it. Real problems, realistic solutions. A.G. Projects.